evening. I welcome you all for the week 12 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Now let's get on to the session. So as usual, let's go through the brief recap of lectures of week 12. So week 12 lectures were on polymers and environment, and the entire week lectures were on biodegradation, biodegradable polymers. Lecture 84 was on microplastics, aerosols and sediments, which was on sustainability aspect of the course. So the lecture started with freight and transport of polymers in environment. How are they released? For example, they are of low density, so they can, for example, if they are in water, they can float through and go move over long distances, and also they have a long life since their degradation mechanism is very slow or they are not degraded. And they vary in sizes. They may be macroplastics as such, kind of a complete plastic chair that is thrown away, or they can be meso or micro or even nanoplastics, which are micro and nanoplastics are very small fragments of polymers. uh, and then there was a discussion on origin, uh, that is the primary and secondary origin of these macro, meso, and micro and nanoplastics, and the impact of the environment. Uh, for example, how does the size actually impact? Because their size vary, widely. They range from 1 micrometer to 5 millimeter. Most commonly between 20 micrometer to 1 millimeter in size. And then uh, uh, they also vary in, so origin, and also they vary in shapes, like they can be fibers, they can be discs or spherical or irregular in shape. The shape depends on the particular application in which they are used, and also it depends on how they are degraded also. Sometimes they may be in a particular shape, but due to degradation over time, due to exposure to different environmental conditions like temperature, or say for example water or some radiations, they may also, due to degradation, they may also vary in size, and also they are insoluble in water. And how does the surface and volume ratio also impact their interaction with the surroundings? And they can impact in various ways. They can be absorbed, they can absorb, for example, moisture, or any other material, like small molecules, or small molecules can leach away from the polymers as well. And then they change the properties. For example, they can change the properties of water, land and air. For example, the oxygen availability can be impaired. For example, they can become a barrier for available oxygen, in, for example, in water. And they also affect the health on fauna. They, uh, uh, they can be, they can get into the uh, system of, fauna, that is animals, through ingestion. And also, their interaction with the surroundings. For example, the ocean systems, there was a discussion on, the presence of these plastics, microplastics in ocean. It was discussed in the lecture that the amount of microplastics present in ocean bed is much larger than that is present in the surface of the ocean, though they are lower in the density and they tend to float over the period of time. They also start sinking due to different interactions. So their interaction can vary. There can be some adhesion, bonding, biofouling, and then some phytoplankton and they can affect as well. And they also sediment, and finally they also settle. And where are the microplastics prevalent? They are prevalent in water bodies. They are prevalent in digestive tracts of vertebrates and invertebrates. They are present in terrestrial environments like soil, sediments, ice caps. They are also present in atmosphere, like in aerosols. Due to their low density and small size, the microplastics are also prevalent in atmosphere in the form of aerosols. So these were the part of major discussions. And how to really avoid these prevalence of these microplastics and their impact on environment. For example, why can't we move from a non-biodegradable to a biodegradable microplastic was also a part of discussion in the lecture. The next lecture was on biodegradation of polymers. This was again on sustainability aspects. So, what are the type of degradation of polymers in environment? For example, a polymer can degrade when it gets exposed to atmospheric conditions such as light or air, or sometimes even when they are exposed to land or water also. These external factors also lead to degradation. For example, a UV exposure may lead to a cross linking of the chains, or they may also lead to chain scission. They may lead to oxidation, hydrolysis, and also there are thermal and mechanical form of degradation. For example, in terms of thermal, hot and cold condition can cause some degradation, and then pressure, wind, and abrasion, fragmentations. So these things can also happen. And then there was a discussion on biodegradation, and then sedimentation transformation. Uh, and then the next part of the discussion were on biodegradation. So what are the factors that affect the factors involved in the biodegradation process? See, for example, what is the mode of disposal, or what is the surrounding conditions? For example, a sewage treatment or composting, or is it an aerobic or anaerobic condition? So all these things affect the biodegradation. For example, the rate of degradation. What are the end products? End products may also have slight variation. What are the intermediate products? So intermediate products can be, in biodegradation, it can be biomass or humic materials. And then what is the exotoxicity of the intermediate products? These were all part of discussion. And then what are the stages in biodegradation? For example, there will be a breakdown due to involvement of enzymes, and then there will be aid by acids and peroxides. So byproducts of the biological pathways. And then they proceed. The next step would be chain cleavage through hydrolysis or photo or even thermal oxidation. Then there will be some formation of products. It may be either a monomer or an oligomer, or their derivatives also. And then finally they get into the metabolic pathway or energy, metabolic pathway or metabolic energy. And then what are the conditions that affects biodegradation? So humidity may affect, and then temperature, pH, salt and ionic conditions, concentration of oxygen, whether it is an aerobic condition, that is with the presence of oxygen, or anaerobic condition, absence of oxygen. So all these things can affect it. And also presence of various other nutrients also, because biodegradation, it may happen through the presence of some microorganisms. So these microorganisms need some additional nutrients also. The presence of those nutrients also will affect the biodegradation process. And how does the structure and properties of polymers actually affect? The molar mass of the polymer itself plays a critical role in biodegradation process. And then the reactivity, the morphology, for example, the crystallinity, whether it is semi-crystalline or completely amorphous, or whether it is cross-linked or not cross-linked, whether it is pure or it has some plasticizers or other additives. And how effective is the diffusion? For example, diffusion of water or diffusion of oxygen or diffusion of any other small molecules or solvent molecules. And then what is the porosity, what is the mechanical strength, stability in thermal and UV conditions or different environmental conditions. So these things can also affect the biodegradation process. So then there was a discussion on what are the biodegradable polymers, and different biodegradable polymers like polyhydroxyalkonates, especially butyrates, and then starch based polymers, and then blends with starch, lactic acid based polymers like your polylactic acid, polyesters like aliphatic and aliphatic aromatic polyesters, and other natural plant derived or microorganism derived polymers like cellulose, xanthan gum, casein, and then collagen, pectin. So there was a brief recap on these biodegradable polymers as well. And then uh, you know uh, what are the points of consideration for a biodegradable polymers and polymeric waste management. For example, the material cost itself and duration of biodegradation. How fast is the biodegradation process in comparison to the accumulation of the polymers, and biodegradation in landfills which are totally isolated. For example, there is no exposure to moisture or air in case of landfills. Especially this is required in order to avoid avoid migration of hazardous materials, especially in the case of landfills. And then what about the scenario of recycling? So for example, there may be a difficulty in recycling uh, you know biodegradable polymers, whereas non-biodegradable polymers may be better in recycling. So what happens if both are mixed together? So whether they'll become non-recyclable or they are not suitable for biodegradation at all if when they are mixed. So these aspects were all brought into discussion in this lecture. The next lecture was on biodegradable polymers 1. This was again on sustainability. So, what are the polymers with biological relevance? So, they can be biodegradable polymers. What are the related terms? And then there was a discussion on what are biodegradable polymers with examples. So, for example, polymers of biological relevance, they may be biopolymers, from natural sources like plants or animals or microorganisms, or there can be bio-based polymers also, which are made from natural sources as opposed to petroleum based sources. Or there can be biodegradable polymers, and these biodegradable polymers can be biopolymers, they can be bio-based polymers, or even polymers from petroleum based sources. Then there was a discussion on composting, and then what are the products in case of an aerobic and anaerobic biodegradation uh, of polymers. And then what are the claims that are put forth in terms of biodegradation? For example, degradation with environment, they can be photodegradable or oxo-degradable. Sometimes they may also say it's partially degradable or eventually it is biodegradable, which cannot be accepted really, because it may take quite a long time. Or if it is partially degradable also, anyway you end up with some non-degradable material. And then what is the toxicity of the intermediate products during biodegradation? And then what is the weight loss, molar mass reduction, mechanical property loss as a measure of biodegradation is not acceptable. And then there was a discussion on composting. Next, there was a discussion on how the biodegradation process takes place in case of a polyhydroxybutyrate. What are the products? The products may be again oligomers or dimers or monomers. So hydrolyze enzymes, uh, PHA depolymerases, that is polyhydroxyalkonates depolymerases, which can be either extracellular or intracellular enzymes that plays a vital role in the biodegradation of polyhydroxybutyrates. What are the final products? So they can be energy, carbon dioxide and water in case of aerobic, or energy, methane and water in case of anaerobic biodegradation of polyhydroxybutyrates. And then what is the duration, how the duration varies with for example, whether it is happening in aerobic condition or anaerobic condition, or whether it is happening in a marine condition, or in a tap water condition. So these were all discussed. And then the next was on biodegradation of polylactic acid. So how does a biodegradation of polylactic acid takes place, and what are the steps, and how long does biodegradation of polylactic acid takes place in an aerobic and anaerobic conditions. So these were all points that were discussed in the lecture. The next part of discussion was on starch-based biopolymeric systems. What are the sources of starches? So source of starch can be, corn or wheat or potato or even tapioca or rice. So these are all, wide variety of sources, which are all plant-based sources, of course. And then, what is the, composition of the starch, and whether it is semi-crystalline, and, how does it reorganize when exposed to water and heating, and how is starch used in several applications. So there can be starch based bioplastics, or starch derived monomers also. Starch, instead of using it directly, you can actually derive different monomers from starch. Monomers are intermediate from starch, and which can be further polymerized and can be used for different applications. And what are the value additions done for starch products? Like, for example, you can add a antimicrobial agent, or you can blend with other polymers like PVA or other proteins, in order to have much more better processability and improvement in the functionality. So these aspects were discussed in the biodegradable polymers 1. The final lecture was on biodegradable polymers 2. This was on uses. So this was basically on application and processing. So in this lecture, what are the promising application in case of starch, or in case of polyhydroxybutyrate or alkonates or polylactic acid, were all discussed. So how do you develop biodegradable polymer, how to make it, ensure that the processing will be easier in case of biodegradable polymer, how do you exhibit good performance and cost competitive uh, materials in case of biodegradable polymer. So these aspects were brought into a picture. And then organic recycling or bio recycling, how can you bring about in place of mechanical or chemical recycling. And then what are the processing of biodegradable polymers? For example, you can use extrusion, film blowing, for example, extrusion in case of polyhydroxybutyrates, or film blowing in case of polylactic acid or polyhydroxybutyrates, or fiber spinning in polylactic acid, were discussed. And then what is the current worldwide market of biodegradable polymers? It was discussed. It was actually shown that it's less than 0.5% of the total polymeric material, because you cannot really match the some of the disadvantages or some of the challenges in case of biodegradable polymers that the current research is going through is the ease of processing of biodegradable polymers is not as that of the synthetic polymers like your polyethylene or polyethylene terephthalate, etc. And what are the next was the discussion on for promising application of starch. So here first the discussion started with what are the key challenges in in application of starch in commercial materials. For example, the difficulty in processing and optimization of the performances. And then there were also, though there are certain challenges, still starch based materials are also brought into applications like shopping bags or disposable bags, utensils. It is also used in mulch films in agriculture, and it is also used in automotive industry, interior parts, and even in medicine like your bone cement or drug release films foams. The next discussion was on polyhydroxybutyrates. Again, what are the key challenges involved in polyhydroxybutyrates? For especially, in case of polyhydroxybutyrates, it is actually produced by microorganisms. So, since it is produced by microorganisms, the yield may not be that much. So you end up with spending more cost in polymerization and producing polyhydroxybutirates. And what are the other challenges in case of polyhydroxybutirates, and where all it is being applied so far? Say for example, they are used in oxygen barrier films, they are used in biomedical devices, and they are also used as blends in packaging. The next discussion was on polylactic acid. And then what are the key challenges in commercial application of polylactic acid was discussed. The next was, where is it actually applied? For example, they are used in non-woven materials, like it is used in, sanitary napkins or diapers, cleaning tissues and clothing. They are also used in, packaging materials, thermoformed food containers, bottles, biomedical devices. So these are various applications where polylactic acid is being used. The next discussion was on biodegradable polyesters. So where there was a discussion on polybutylene succinate and polybutylene adipate terephthalate. And their glass transition temperature and melting temperature of polybutylene succinate was discussed. And where is it applied? It is again used in mulch films. And then the next discussion was on polybutylene adipate terephthalate. And then the lecture concluded with a discussion on, so far the discussions were all on biodegradable thermoplastics. So what about bringing biodegradable thermosets and elastomers? Say for example, what about the thought of using, vegetable oils for synthesis of epoxy resins, and non-isocyanate based polyurethanes, unsaturated polyesters. So, instead of using toxic reagents, why can't we move into non-toxic materials? And how does it affect the property? And how does it help in biodegradation? So, these thought processes and all were discussed in the lecture, and the lecture was concluded. Now, let's get on to the practice assignment session for week 12. Select the origin, whether it is primary or secondary, for given set of, sorry, there's a typo error. Just hold on for a moment. So, select the origin, primary origin or is it a secondary origin for a given set of mesoplastics, microplastics and nanoplastics. Ink, whether it is a primary source of origin or is it secondary. Film embrittlement, personal care products, tire abrasion. So, what are the source of origin? So, is it directly available as meso, micro, or nanoplastics, or is it getting converted? That is it secondary origin? That is, it is getting converted to meso, micro, or nanoplastics due to certain processes that is happening due to some certain exposures. So, the answer for this is first ink. Ink, it is a primary source. Here, the meso, micro, or nanoplastics are available. So you have, microplastics or micro or nano-sized, polymeric particles in the ink directly. So it is a primary source of origin of micro or nanoplastic or mesoplastic. Whereas in film embrittlement, it is a secondary source because film as such, it is a macro size shape, but due to some, exposure and, exposure to either it can be a thermal exposure or a UV exposure or certain other, environmental exposure, it becomes embrittled. So that leads to, uh, uh, you know, because it is not the first stage, but it is due to some certain, kind of exposure or processing that leads to these microplastics. So that means it is a secondary source. Personal care products are again, it is a primary source. Because again in these personal care products there may be micro or nanoplastics directly in the material itself, and this lead, leads to the primary source of these micro or nanoplastics. And tire abrasion, again due to some abrasion process, uh, yeah, if this happens, so this is again a secondary source of so you get finer particles because of the abrasion of the tires. So you end up with micro or nanoplastics, because as this tire is a macroplastic, right? A tire is a big component. So but due to some abrasion process, because you you use it on roads, right? Or maybe once it is used and thrown off, it may be exposed to certain environmental conditions. So because of those abrasion process and all, you will have finer micro or nanoplastics. So you end up as a secondary source. Next, microplastics have also been identified in digestive tracts of vertebrates and invertebrates. Identify if the statement is true. Is it true that the microplastics have even been found in digestive tracts of vertebrates and invertebrates? Has it gotten into the digestive system? Really, these plastics? Is it really true? The answer is yes, it is true. These microplastics have gone into the digestive tracts of vertebrates and invertebrates. We have actually seen, when you just walk through the road, you see cow eating plastics, right? Cow or other animals, it starts uh, eating something from the dustbin, right? The big waste bins in the roads, and that will have a mix of all these plastic covers, polythene covers, your milk covers, etc. And these since they tend to eat these things and all, they enter into the digestive tract, and due to some high acidic environment in your digestive juices and all, they may again break down to certain extent, and thus you find these microplastics even in the digestive tracts of vertebrates and invertebrates. So it is very alarming, right? So in fact, these prevalence of microplastics is there in water bodies, it is there in oceans, lakes, rivers, shorelines, swamps, in digestive tracts of vertebrates and invertebrates. They are present in terrestrial environment like soil, sediments, and ice caps. They are also present in atmosphere in the form of aerosols. So even the air we breathe in, it will have certain microplastics suspended in it, and we tend to breathe in that also. That may also enter into our system. So which is all very alarming, right? So there is a utmost necessity that we have to avoid this prevalence of these microplastics, such as polyethylene or polypropylene or PET, PVC microplastics in the environment. Maybe we have to move towards more biodegradable polymers. Next question. Microplastics have lower surface to volume ratio that leads to increased interaction with the environment. Is it true or false? Do they have low surface to volume ratio that actually leads to increased interaction with the environment? It is actually false. The microplastics, they have higher surface to volume ratio. They have huge surface to volume ratio. For example, you can see in this image that a 5 sheet has a surface to volume ratio of 440 meter square per second. So sorry, meter square per meter cube, sorry, surface to volume ratio, so meter square per meter cube. So for 1 meter cube you have a surface area of 440 meter square. And if you just compare it with a 50 micrometer particle, it is quite alarming that the surface to volume ratio, it increases like phenomenally. You could see that a 50 micrometer particle has 1 into 10 power 5 meter square per meter cube. So this much of surface is exposed and for interaction with the environment. So the more the surface exposed, surface to volume ratio, that means the more surface you have, is exposed to the environment, and they have a huge amount of interaction with the environment. So we have to, be very conscious on this and try to avoid these microplastics in the environment. We could see from 440 meter square per meter cube in case of a 5 sheet, to 1 into 10 power 5 meter square per meter cube for a 50 micrometer particle. How much variation you would and this, the large surface area is exposed, so the more the interaction, so larger part of surface is getting exposed to the environment, and it will have much more interaction with the environment, whether it is going to be a moisture, or whether it is going to be a UV light, or whether it is going to be water body water, or it is going to be air. So their exposure will be much more, and their interaction will be much more, and their impact will be much more. Reassociation of starch molecules when gelatinized starch is cooled is referred to as, what do we call reassociation of starch molecule when a gelatinized starch is cooled? What is this process called? This process is called as retrogradation. Okay. Next. Arrange the biodegradation of polyhydroxybutyrate in the increasing order of its duration. Anaerobic biodegradation, marine degradation, bacterial degradation, and tap water. So which takes shortest time and which takes longest time in case of biodegradation of polyhydroxybutyrate? So does bacterial degradation takes the shortest time, or does anaerobic biodegradation takes the shortest time, or does marine degradation takes the shortest time? This was again discussed in the lecture. So the answer is bacterial degradation in tap water takes the shortest time. It takes only 40 days for biodegrading polyhydroxybutyrate using a bacteria in tap water. Whereas anaerobic degradation may take few months. And marine degradation, it takes years. So even in case of a biodegradable polymer, when the environment is changed, when the conditions are changed, their level of biodegradability varies, prominently, right? So when you have a bacterial degradation, the work gets over in 40 days. Whereas when it is a marine degradation, again, this is going to take years. So if it is going to get into the depth of ocean in the marine environment, it's going to take years, even for a biodegradable polymer. So what is the case of non-biodegradable polymer? We have to think on that. And we should start thinking about alternatives. The first step in aerobic degradation of polylactic acid is, what is this first step in aerobic degradation of polylactic acid? The answer is hydrolysis. So, polylactic acid has these ester bonds. You could see the CO bonds. So, addition of water, it helps in hydrolysis. So, you end up forming acid and alcohol. So, this is the first step in the aerobic degradation of polylactic acid. Hydrolysis is the first step. So, breaking down the ester bonds into acid and alcohol bonds. Next. One of the key challenges in application of polylactic acid is, what is the key challenge? One of the key challenge in using polylactic acid extensively. What is it that is forming the hurdle in wide application of polylactic acid? The key challenge is controlling the stereochemistry of polylactic acid. So you can end up with L and D enantiomers. And in case of polylactic acid, the D enantiomer has high crystallinity and its biodegradation is comparatively slower. Okay, so the stereochemistry. So maintaining the stereochemistry is little difficult. because there's a probability of forming both L and D enantiomers. And one more disadvantage of having a D enantiomer is that it is having high crystallinity and the level of degradation, because as the crystallinity is more, the access for microorganism to break it down is lesser. So amorphous region can be easily broken down, whereas the crystalline region, it needs much more. It is much more complicated to break it down, since you have this lamella arrangement and all, right? So because of much more ordered arrangement and packed arrangement, the crystallinity is higher, and eventually the biodegradation process is also slower when you have a de-enantiomer in case of polylactic acid. Next, petroleum based polymers are all non-biodegradable. Is it true or false? So are all petroleum based polymers non-biodegradable, or are there certain petroleum based polymers? We know that petroleum based polymers are, the source of the petroleum based is a petroleum is a non renewable energy. So does that mean that one that is coming from a non renewable source, the polymer coming from that is always non biodegradable, or are there examples where they are also biodegradable? The answer is it's false. That means there are polymers from petroleum sources which are biodegradable. For example, biodegradable polyesters, polybutylene succinate, which is actually a biodegradable polyester, which was discussed in the final lecture on biodegradable polyesters. In fact, two polyesters were discussed. One was polybutylene succinate, and one was polybutylene adipate terephthalate, PBAT. Okay. Starch is composed of dash and dash. What is the composition of starch? What are the monomers present in starch? The answer is starch is composed of linear amylose, which is 20 to 30%, and branched amylopectin. Again, sorry, there's a typo error. It is branched. Branched amylopectin. So this is the structure of amylose. You could see the chain is very linear, whereas in case of amylopectin, you have a branching. Okay. So this is the composition of starch. So where amylose, 20 to 30% of starch is made up of amylose, and the remaining 70 to 80% is made up of amylopectin. Okay. Strength or strain at failure of pure polybutylene adipate terephthalate (PBAT), a biodegradable polymer, is similar to what? Which synthetic polymer? Strain at failure of polybutylene adipate terephthalate. This is again a biodegradable polyester. So the strain at failure or strength of this PBAT is similar to one of the synthetic polymers. Which polymer is that? It is actually similar to LDPE. That means we can also synthesize, biodegradable polymers which have similar properties to that of other synthetic, commercially available and extensively used non-biodegradable polymers like LDPE. But of course, there are other challenges. So here the strength or strain at failure is similar, but there may be other challenges associated with the PBAT that may make it a little difficult to, replace, uh, you know, LDPE. But still, there will, we have to, really work on that, so that we can eliminate these non-biodegradable polymers like LDPE and all from the environment, and their impact can be reduced. Okay, next, polyhydroxybutyrate is brittle in nature. Identify the key challenge in application of polyhydroxybutyrate based on the discussion in lecture 87, and also related to the brittle nature based on your knowledge of stress strain curves. So in lecture 87, there was a discussion on polyhydroxybutyrate, especially on the key challenge in application of polyhydroxybutyrate. In fact, one of the challenge we discussed that it is from the microbial source. It is from the it is produced by a microorganism, so the yield may be very less. So since the yield is less, so you may end up with a higher cost of polymerization, because in order to produce a larger quantity, you have to use larger input and everything. So obviously you will end up with higher cost. So cost is one of the key challenge. But what is the other challenge, especially related to the brittle nature of polyhydroxybutyrate? So you can relate this based on your knowledge on stress strain curves. How does the curve of a brittle polymer looks like? Stress strain curve look for a brittle polymer, and from that you can identify what is the key challenge associated with the PHP. So answer is, the brittleness of PHB is due to the formation of large crystalline domains in the form of spherulites. Okay, since there are large crystalline domains, the PHB is brittle in nature, and this the key challenge in application of polyhydroxybutyrate is its toughness. So, how do you relate the brittle nature and the toughness? So, toughness is nothing but energy absorbed before failure, and it is given by area under the stress strain curve. And you can just observe the toughness for and area under the stress strain curve for brittle, ductile, and flexible polymer. And if you look into the curve in general, for a brittle polymer, the area under the stress strain curve is very small. That means the toughness of the material is very less, and this is what is a key challenge associated. So since the toughness or energy absorption before failure is the toughness is very less, it makes it challenging uh, to use polyhydroxybutyrate in commercial application. And this brittle nature of polyhydroxybutyrate is basically because of the large crystalline domains, and they tend to form spherulites. So because of the large crystalline domains, they are brittle in nature, and this brittleness leads to a lower toughness, where brittle polymers show lower toughness. Next. Hope you understood. So for a brittle polymer, the area under the stress strain curve is very small. That means the toughness is very less. And this, because of this low toughness is a key challenge in application of the polyhydroxybutyrate. Next. Pectin is a bio-based polymer. Is it true or is it false? Is it a bio-based polymer? Pectin? There was a lot of discussion on pectin in one of the earlier lectures, and this the lectures of week 12, there was a highlight on pectin also. So is it a bio-based polymer? It is actually a biopolymer from plants. It is not bio-based, but it is a biopolymer from plants. The source itself is from nature, from plants. So it is present in middle lamella and cell wall of plants. Pectin is present in abundance in middle lamella and cell wall of plants. Next. Growth of microorganisms can be used as a measure of biodegradation. So if you see microorganism growing in a plastic material, does that mean that the plastic material is being degraded by biodegradation process? Is it true? This presence of microorganism on a plastic surface, for example, means that my particular microorganism is degrading that particular plastic, and we can say that there is a biodegradation happening in that plastic material. Is it true? It is actually false. Growth of microorganisms on plastic material, it does not mean there's a biodegradation. See, for example, you may have a plastic container and you would have eaten some food. Okay, there may be some food residue and you would have left it, and because of the food residue present, there may be growth of microorganisms. Microorganism is growing because of the food residue. Maybe you would have eaten some sweet, or you would have eaten some rice in that, so it is going to degrade that leftover rice or leftover food. That does not mean it is going to degrade the plastic bowl. So that does not mean that there is a biodegradation of the plastic bowl because of the microorganism present. So weight loss or degradation, weight loss or disintegration or growth of microorganism, it does not mean there is a biodegradation happening. Okay, so weight loss or molar mass reduction or mechanical property loss as a measure of biodegradation is not acceptable. So there can be, you may find a weight loss due to several other reasons. So there may be some exposure to for example, thermal radiation. Okay, so because of that, there may be some chain cleavage, and that may lead to some molar mass reduction, and the mechanical property reduction may be there. That does not mean that biodegradation is happening. Similarly, as I said, you may have a bowl, where you have some leftover rice, and the microorganism may start growing because of the leftover rice. It does not mean that the plastic bowl is being biodegraded. The microorganism is growing because you have left some rice in that bowl, and it is going to eat that rice and survive. It is not going to really eat away your plastic bowl and degrade it. Okay, now the next question. Arrange the degradation steps of polylactic acid in the presence of water. So polylactic acid degrades in the presence of water. So what are the steps involved? What is the sequence of steps that happens? So there are 4 steps given. We have to arrange these steps in the order. So the 4 steps given are hydrolysis of crystalline domain due to increased acid concentration, decrease in molar mass of amorphous domains, diffusion of water in PLA, hydrolysis of amorphous domains. It's not hydrolysis is amorphous domains, it is hydrolysis of amorphous domains. There are some typo errors, sorry for that. So what is the sequence of steps actually happening? So we have to arrange these steps. Hydrolysis of crystalline domain due to increased acid concentration, decreasing molar mass of amorphous domains, diffusion of water in PLA, hydrolysis of amorphous domains. Which of these steps happens first? Which is the sequence of steps that happens for degradation of PLA in the presence of water? What should really happen first to start of the process? Water is there, PLA is there. What should happen first? So the sequence of steps are as follows. First of all, water is there, polylactic acid is there. But this water has to diffuse into polylactic acid for the degradation process to start off. And then once it starts diffusing, there is a hydrolysis in the amorphous domains. Because you have polylactic acid, so the the ester bonds, the polylactate ester bonds, starts getting hydrolyzed to acid and alcohol. Okay, so hydrolysis of amorphous domains. So first, the easiest domain to attack is your amorphous domain, which gets, you know uh, which can be altered easily is your amorphous domain. So after water starts diffusing, then the next step that takes place is the hydrolysis of the amorphous domain. And then, because your amorphous domain is getting hydrolyzed to acid and alcohol, because we have seen in the previous, in previous one of the questions, how the hydrolysis happens. So hydrolysis, so you have the ester bond, COO bond, and because of the presence of water, it gets converted to COOH and OH. So after this, because of the hydrolysis of the amorphous domain, there will be a reduction in molar mass of the amorphous domain. So once there is reduction in molar mass, and the final step that takes place is hydrolysis of crystalline domains due to increased acid concentration. Because when you start hydrolyzing the amorphous domain, we just saw that it gets hydrolyzed to acid and alcohol. So because of this presence of acid, and since the amorphous domain keeps on getting hydrolyzed, and more acid is produced, then because of the presence of this acid, the crystalline domain can be broken down, and hydrolysis of the crystalline domain starts happening. So these are the steps. First of all, the water has to diffuse, then it has to then hydrolysis reaction takes place in the amorphous domain, breaking the ester bond into acid and alcohol bonds, and this leads to decrease in molar mass of the amorphous domain. And finally, when you have more and more production of acid due to the breakage of ester bonds, you will have more and more acid, then this leads to hydrolysis of the crystalline domains. Okay, so these are the steps of degradation of polylactic acid in the presence of water. Next, a promising factor for biodegradation is rate of degradation is greater than rate of accumulation. Is it true or false? So, if the rate of biodegradation is more than the rate of accumulation of that particular polymer material, then the biodegradation is a promising method, to get rid of that particular polymer. Is it true or false? It's actually true. So since the rate of degradation, is more than the rate of accumulation. So as your, the used waste polymer gets accumulated, but at certain rate, but the rate of degradation of already accumulated biopolymer, sorry, already accumulated polymer is much more than the rate it is getting accumulated in the environment. Obviously, it will easily get broken down, as soon as you have an input of this waste polymer, it will start degrading faster also. So you don't end up with a large accumulated waste biopolymer, sorry, waste polymer. Okay, because it is getting you can easily biodegrade it. Okay, so this is actually a requirement also. Okay, compared to other degradation, if your rate of degradation is greater than rate of accumulation, then it is a very promising, this biodegradation method is a very promising method to get rid of that waste polymer. Okay, next, fragmentation of macromolecules is the first step for utilization as carbon source by microorganism. So should the macromolecules get fragmented in order for the microorganism to use it as a carbon source and take it into the biogeochemical cycle? Yes. Fragmentation of macromolecules is the first step for utilization as a carbon source by microorganisms. Because macromolecules, as the name itself suggests, they are very large molecules and they cannot be used as such as a food source by microorganism or any other biological species also. So therefore, you have to fragment it. You have to break it down into smaller segments. I mean, smaller entities as a first step before it is being utilized by the microorganism or any other biological species as a carbon source or as a food. Okay, so that So this means that the chain cleavage, the macromolecule should be broken down into smaller chains. Is very important aspect. So chain cleavage can happen through enzymatic process, especially for biodegradation. Enzymatic process of breaking large macromolecules into smaller fragments is very important, so that it can be used as a food source by microorganism, and then they can be brought into the biogeochemical cycle, breaking down further and further, and then you will end up with carbon dioxide and water. Okay, if it is aerobic, or methane and water if it is an anaerobic process. Or this fragmentation can also happen through hydrolysis. Okay, or it can also happen through oxidation. For example, in through hydrolysis, we also saw in PLA, right? In PLA, what happens? Due to the presence of water, the ester bond is broken down into acid and alcohol. So this causes the fragmentation of the big polymeric chain into smaller fragments. Okay, and oxidation using other means can also, or you can have a combination of steps. You can use water plus the presence of some enzymes, and then presence of oxygen, all these together, in some combination also, they break the very large macromolecular chain into smaller fragments, which can be further utilized by the microorganisms for complete biodegradation process to take place. Next, anaerobic biodegradation of PLA is faster than aerobic biodegradation. Is it true or is it false? So, anaerobic degradation of PLA is faster than aerobic biodegradation. Is it true? It is actually false. So, anaerobic biodegradation of PLA, it is a very slow process. It may take tens of years. Whereas aerobic biodegradation, it takes few months. So this is again an example that when you change the condition, earlier we saw for polyhydroxybutyrate that in bacterial and tap water condition, it fragments in 1 second. It fragments in minutes. Sorry, in in for 40 days. Whereas if it is going to be your uh, you know uh, marine condition, it is going to take years. And similarly, we are seeing here for PLA that if it is going to be a anaerobic degradation, it is going to take tens of years. Whereas if it is going to be aerobic degradation, it is going to take only few months. Okay, so as we change the condition, even the biodegradation process, the time scale of biodegradation will change. Okay, so we have to optimize which is the best biodegradation process also among different conditions. Okay, next. Toxic intermediates are acceptable in biodegradation. Is it true or false? Is anyone there? Toxic intermediates are acceptable in biodegradation. Is it true or false? Can we have toxic intermediates? It's actually false. You cannot have toxic materials, whether it is going to be your end product or it is going to be your intermediate. In any form, toxic materials in biodegradation, it is not acceptable. Okay, exotoxicity of intermediate products assessment is an essential factor involved in biodegradation, because your intermediate to your final product, it may not be uh, getting converted in fractions of seconds. Sometimes it may take some time, some considerable amount of time. In fact, we saw it takes 40 days for biodegradation of PHB in the presence of bacteria, right? So 40 days there may be some intermediates that are being formed in the midpoint of time. So it may take some quite a bit of time to getting converted into final products. So if this intermediate that is being formed, if it is going to be toxic and it is going to stay for a while, it is actually harming. So it is not actually acceptable. Okay. So toxic intermediates are not acceptable in biodegradation. So exotoxicity of intermediate products assessment is very essential. So you have to assess the exotoxicity of the intermediate products also in a biodegradation process. Okay. Next, bioassimilation and mineralization is a final step in biological degradation process. Is it true or false? Is bioassimilation and mineralization the final step in biological degradation process? It's actually true. So your assimilation, so it finally gets assimilated and mineralized also. The leftover minerals also, no, mineralization also is a final step in biological degradation process. Okay. Next, a natural process by which organic materials are decomposed by microorganisms or small insects or earthworms or by other soil inhabiting organisms to produce humus. A soil like substance is called. What is this process called? A process in which it is a natural process by which organic materials are decomposed either by microorganisms or small insects or earthworms or some other soil inhabiting organisms to produce humus, a soil like substance. What is this process called? So this process is called as composting. Composting is a natural process by which organic materials are decomposed by microorganisms or small insects or earthworms and other soil inhabiting organisms to produce humus, a soil like substance. In fact, this composting with earthworms and all, you would have seen videos and all, composting using earthworms, where you grow earthworms in a compost. Okay, this is, you end up with the final product which is called as humus. It looks like soil. Okay, and it is used as a fertilizer also. Okay, in agriculture. Okay, so that's it with the session. Thank you all. Just hold on a moment. So you want to know the techniques how to select the base polymer or host polymer, right? So for energy storage. So energy storage, obviously, there was a discussion on this dielectric properties of polymers, right? So in dielectric properties, your dielectric permittivity E prime, it denotes the energy storage, right? And E double prime, it denotes your energy dissipation. So you have to look into polymers which are dielectric in nature. So you have to go through those lecture, those literature which discusses on dielectric polymers. So and then check into the energy storage of those polymers. And especially, if you are looking into biopolymers, then you have to further fine tune your search based on what are the biopolymers that are used for energy storage applications and all. Okay, so in that way you can just streamline those polymers. Okay, hope you are clear, right?
Yes, ma'am. Thank you.
Okay. And then your previous doubt was on gels, right? As you had asked, the gels tend to dry, so you have to look into the, how fast is the rate of drying also. In fact, swelling and drying of gels is also one of the studies which are performed, to understand the behavior of gels. So how fast it dries and how fast it swells. So that test is also done for understanding the gel systems. Okay. And if you find it drying within days, maybe you have to look into do any kind of characterization, for example your rheological characterization and all. If you see it drying after 1 day or something and all, no, try to do the rheological characterization within a day and see how it is. And if drying is really happening, sometimes it may look so but it may not be the case. Or else you can store these gels in water. So for example, if you form some kind of a thin disc of these yeah, your hydrogels, you can just place it in water or some solvent medium so that it doesn't evaporate till you do the test. So that is one of way of storing and avoiding evaporation. In fact, for example, when you're doing these rheological tests and all, no, sometimes this one single test may take like 45 minutes or 1 hour also. Sometimes it may also take 2 hours or something, depending on the test and uh, what is the frequency you give and all, no. If it is an oscillatory test, the oscillating angular frequency, whatever you give, the test may take quite a bit of time. If you go for very low frequency and all, no, it may take quite a bit of time. So in under those conditions, what we generally do for rheometer is that we tend to add a solvent trap. And commonly used solvent trap is like, you may add a, you have seen in the lecture, right? In cone and plate rheometer, you have a bottom plate and a conical top plate, which rotates or oscillates. So you place a sample in between that, and just surrounding that plate, people tend to add a small layer of silicone oil, or in some cases they tend to add mineral oil, or in some cases, they also add water, around, so that it avoids evaporation during the test itself. Even if you go through the literatures, no, they would have mentioned that they have added layer of silicone oil trap or solvent trap to avoid evaporation during the test. So hydrogels are always prone to this drying, so we have to see, how fast is the drying rate and all, and then based on that you can do the test. And obviously you will have degradation also. So we have to see, how long you can keep and do the test. For example, if it is going to get biodegraded by microorganism and all, no, you cannot store it in room temperature and then do the test for you prepare the gel today, and after 1 month, if it is going to be some natural polymer like alginate based gel and all, no, uh, you cannot just store it in some random temperature or room temperature or expose it to some environment and then do the test uh, after a longer time. We have to find out, how fast it gets degraded, and based on that we have to complete the test in that stipulated time. Okay. Hope you're clear with that. Any other doubts? They are drying. I'm really not sure. Okay. See, based on the presence of water and removal of water, also, no, they may have some kind of those dielectric behavior. Also, you will have to go through the respective literature. So if you go through this respective literature, no, you will you know get to know these things and all. Okay. Or else, maybe you can post these questions in the forum also. If there may be chances that the professor answers it in a better way also. Or maybe in the next session I'll try to answer some of these questions if tend to find some answers. Okay. Any other doubts? Okay then. So fine. Hope you are going through the lectures and you don't have any doubts in the lecture content as such. Revati?
Yes, ma'am.
So I don't think you have any doubts in the lecture content and all, right?
No, ma'am. They are all clear. Nice.
Okay, fine, fine. Hope you are able to solve the assignments also, and the the problem solving sessions are also useful for you, I guess.
Yes, yes, ma'am.
Okay, in case no further doubts, maybe then we can officially close the session. Okay, and maybe next week, try to join the session at least, the session is from 4 to 6. At least if you start joining at 4:30, it's fine. Okay, because I tend to wait till at least for half an hour if I could see someone joining or not. Okay, so try to
Okay.
okay, yeah. Then that's it for the day. Thank you. Have a nice weekend.
Thank you.
Thank you.